Welcome back. All right, we've got more work to do in our design. We're gonna go back to the lighting designer, or the lighting controller, I should say, that we were working with previously. The new concepts we're going to use in this section, we're going to be receiving message with our TCP connection. We're using the receive message block that gathers data from a third-party device. We're going to be creating substrings. A substring is a smaller string that you take from a larger string, a substring. We're going to create timers. We've done simple timers before where we just did like a call after timer. This time we're going to create an actual timer that runs and has an event handler and can be started and stopped independently. And we're also going to use the log blocks where we will be sending certain messages up to our core manager to report that various things have happened. You may remember that when we were controlling our lights, we successfully created a TCP connection. It was really, really easy, and we just sent out a string that changed the lights in the room. That's fine, but it's only one-way communication. We're only sending that data. Now, a lot of times one-way communication is fine. You hit the button and you can see that the lights changed. Awesome, that is your confirmation that the thing you did actually was successful. But in this case, we do want two-way communication. We want information coming back from the device so that we can update our UCI and make sure that our UCI is always married to the actual settings in the room. Why would we need this? Well, if you're a human, which you very likely are, when you walk into a room and you want to turn the lights on and off, where are you going? You're probably not first going to the touch panel on the desk to change the lights. You're probably looking for a switch on the wall, right? And if someone does change the lights manually in this room, on or off, then the lights have now changed in the room. But on our UCI, the previous setting that someone just pressed is still active. We want the lighting controller to talk back to our design to update the buttons so that those buttons actually reflect the lighting in the room. And it's not just the lighting controller on the wall. There might be other things in our design that might change the lights. Later on, maybe we're going to add a function that's, when you start playing some media in the room, the lights automatically dim. And that's automated, but it doesn't have to do with the buttons you're literally pressing on the UCI. It's some other activity. We want to make sure that anything that could potentially change the lights in the room, whether it's a human or whether it's something else in our script, will get that data coming back to our system. But in order to do that, we need to understand what information the lighting controller is sending to us. Now, you may recall in the design, we can look at our lighting API, and it tells us that when we do, ask for something, it's going to give us LVL at XX. That's the response. That's what it sends from the lighting controller to us. LVL at XX. And we talked about XX previously. Those are the two numbers that represent the current settings, 0 to 99. But what it's sending to us isn't actually numbers. It's actually sending us a string. A string are characters. And we need to be able to bring in these characters and understand that we need to convert them into numbers. Well, what do you mean? If it says 99, isn't that already a number? How are you going to convert 99 into a number? 99 is already a number. In order to talk about this, we need to get a little bit better understanding of what strings are at a computational level. So follow me here. So, strings. When we talk about text, something to keep in mind is that every character in a text field is a particular byte of information. So here we've got the word hello friends. The H is a byte of information. The E is a byte of information. The L, etc. Really, really important to note that also the space between these words is also a byte of information. That byte of information says, hey, you're going to separate the previous character from the next character, right? Everything that you type in on your keyboard is a byte of information. Now, digging deeper into that, what does that mean? Computers talk in ones and zeros. We've probably heard this before. And a 1 or a 0 is a bit. A bit can either be on, it's a 1, or it can be off, it's a 0. That's all we got. Binary, on or off, all right? Well, if you put 8 of those together, you have a byte, all right? 8 bits equals a byte. Every single one of the bits in sequence could be a 0, it could be a 1. Now, we're going to analyze that byte and turn it into a number in a very interesting way. The way that it works is every place or every value place in that byte represents 2 to an increasing power of itself. All right, the rightmost byte represents 2 to the power of 0. What's 2 to the power of 0, Jeff?
1.
1, all right? What's 2 to the power of 1?
2.
What's 2 to the power of 2?
4.
Every single time it doubles, right? So this rightmost position represents a 1, this represents a 2, this represents a 4, 8, 16, 32, 64, 128. Now, if you look at that, you could create any number between 0 and 255 through various combinations of these 8 possibilities. If you wanted a 3, you would just want the 1 plus the 2, right? If you want a 7, you could grab the 4 and the 2 and the 1, if you, etc. Every number can be represented by any combination of these, all right? So, looking at our binary at the very top, and we have 0, 1, 1, 0, 0, 0, 1, 1, what those correspond to is if you have a 1, then you do include that number. If you have a 0, you don't include that number when you sum them all up. So we don't add 128, but we do add 64 because we got a 1. We do add 32 because we got a 1. We don't add 16, we don't add 8, we don't add 4, we do add 2, we do add 1. Add all those numbers together, you get the number 99. That's just one example of what a byte might represent. So those 8 bits could potentially represent any number 0 through 255. Good so far? Okay, well, those are numbers. How on earth do we convert these numbers into letters, right? There's no adding up of 2's that will get you the letter B unless you then reference it into a table. So with those 255 options, we basically can then go look in an ASCII table, which will give us an output of some character. Here's an example of 0 through 127, the characters that you could pull out of a table by feeding in a particular number. Now you can probably guess what 26 of those characters are. They're going to be A through Z. Capital A through Z or lowercase a through Z? Well, now we need more than 26. We have 52 of them, right? 52 of these are uppercase or lowercase. But there's way more than just 52 characters in this list. There's all kinds of other things. You will notice some of them are numerals. These are different than the number we're feeding in, right? The entry of number 49 in this ASCII table gives you the character of 1. That's a character of 1, right? That is a symbol. That's all it is. It doesn't have any actual numerical value into itself. It's literally just a symbol. Now, there's lots of other ones on here that don't actually even represent anything at all that you would see visually, because there's other things that you can do while you're typing. You can hit enter, right? You can hit space. And you'll see that some of these are what you might call white characters that aren't shown. And all of these can be represented by throwing a number into the ASCII table and pulling out the character that you want. So what does this mean? What does it mean? Why are we talking about this? Well, here's an example, right? Number 57 on the chart equates to the character 9. And if we showed you this one already, right? 011000 equals 99. Well, if you wanted to show the string of 99, that's different than the number of 99. In order to get the string of 9, you need that entry number 57. So you're going to input 001111001, which translates into the number 57, throw that into the ASCII table, and you pull out the character 9. So if you need the string 99, you need 2 entries of 57. You need 57 once, and 57 again. You get the character 9 out, you get the character 9 out again, you put them together, you have the characters 99. Why do you need to care about this? The reason you need to care about this is fundamentally just the knowledge that numbers and strings are fundamentally different data types. They are just not the same. Whether or not you want to dive deep into binary and really understand everything about ASCII tables and decimals and all that kind of stuff, I don't care. What I need you to care about is that these are different types of information. So even though you as a human might think to yourself, oh, I got 99, that's going to work wherever I need it to, you need to understand that the computer, if it's seeing that 99 as a string, it is just totally different base level information than a number 99. Because you can represent the number 99 with 1 byte of data, with 8 bits, right? You can represent the number 250 with 1 byte of data. But 250 would require 3 bytes of characters if it's a string. Again, they're just fundamentally different beasts. Cool? All right.
They look the same, they smell the same, they ain't the same.
Yeah. Other things to be aware of is there are some commands that you can basically put into a string. Particularly in Lua, the backslash is called an escape character. When your Lua is basically reading the string that you want to print, if it hits a backslash, it's not going to print that as a backslash. It's taking that backslash as a directive to leave what it's normally doing and then read the next character that follows the backslash and use that to look up in its table for something else that it should be doing. It's kind of like the shift key on your keyboard, right? You don't have 52 buttons on your keyboard for lowercase and uppercase characters, right? You have 26. But if you hold the shift and then press another one, you get a different version of a character out. That shift tells your computer that the next thing you do, it should do an alternative version of that button rather than the primary version of that button. So the alternative version of a lowercase r, for instance, when you use an escape key or a backslash r, is to input a carriage return, which is, like hitting enter on your keyboard. It makes a new line, goes down the beginning of it. There's various versions of these. You can create a new line by creating like a feed that goes down. You could use backslash x, which tells us that the next 2 characters after the backslash x should be interpreted as hexadecimal. There's a variety of these. If you actually want a backslash, like if you legitimately really want a backslash, then you do backslash, where it says, hey, don't do the normal thing you do, but instead, oh, never mind, we actually wanted a backslash. So if you ever come across that, that's what you need. Anyways, be aware of those. If you need to input these types of commands, it's probably going to be done with the escape character of a backslash. Okay, so with that in mind, we can now go back into our design and we can figure out what to do with the strings that our lighting controller is sending us.